Hello and welcome back to Mr. Powers Teaches Algebra. So I wanted to talk to you about some results we can get from this division algorithm with polynomials. Some really interesting things and some tricks we can use. So for review here's our division algorithm for polynomials, which pretty much says if p of x and g of x are two polynomials, and we're going to do p of x divided by g of x, well, you're going to get a quotient and remainder. There's our quotient, there's our remainder. So in other words, we can type p of x as, I like to put it here. I'll put the g of x first. G of x times q of x plus our remainder polynomial, plus our remainder, r of x. Now, what if we go ahead and talk about the special case where g of x is of the form x minus r? If that's the case, well, what we get is that p of x can be written as x minus r times q of x plus r of x. All right. What does that mean now for p of r? What happens if I plug in r? In other words, I make this 0. What happens then, right? What is p of r? That's going to be r minus r, in other words, is 0, times q of x. 0 times anything is 0. So all of this is going to be a 0 plus r of x. Well, that's very interesting. P of r is r of x. And actually, r of x is always going to be something to note also in this case. R of x is always going to be a number. It's going to be a constant because we're dividing by x minus r. That's a linear factor. It's a polynomial degree 1. Our remainder has to be polynomial degree 0. That's a constant. So in other words, p of r is going to equal that constant, that remainder that we get. So that's really interesting. In other words, if I wanted to know what my remainder is when I divide by x minus r, I want to know what my remainder will be when I divide by x minus r, I could just plug r into that function. That is really cool. Another result is well, you know what? Let's talk about that first. So we're going to talk about this. So back to this synthetic division. Let's go back to this problem I did earlier, where we divided. Let's see if I can get this. Well, it looks like I got it. Joop. Let's go back to this. Oops. Okay. Let's go back to this guy where I divided here my my p of x, let's say, was 3x cubed minus 5x plus 11. And I divided by x plus 3, right? It was divided by x plus 3. So in other words, my r would have been, right, x plus 3 is the same as x minus negative 3. So I'm dividing by x minus negative 3, or my r is negative 3. So to test this out, we already know my remainder when I did this division was negative 55. That was my remainder right here. So, and I didn't write it up here, but that was my remainder. So according to this little result that I shared up here, I should be able to get that remainder simply by plugging in -3. That should give me the remainder of this problem. The remainder of 3x cubed minus 5x plus 11 divided by x plus 3 should just give me the remainder. All right, so let's see here. So what we get 3 times -3 cubed minus 5 times -3 plus 11. All right. So that's -27 times 3 is -81. -5 times -3 is 15 plus 11. So that, in fact, does equal -55. So that is really cool, and it totally worked. So what is the use of this? Why would we do this? Well, what if you want to know, you have a polynomial, let's say like 3x cubed minus 5x plus 11, and you want to know what is p of 25. What does that equal? So if I plug 25 in here, what do I get? Well, man, I'm going to have to do 25 cubed. That might be rough. That might be really bad, right? It's a big number, right? And we can imagine worse numbers or maybe even bigger polynomials. Maybe I have a polynomial. Maybe my I have f of x is 8x to the 7th plus 2x, right? And I want to know f of 8. What's that equal? I don't know, just off the top of my head. Maybe it would be easier, rather than find f of 8, it might be easier to take this 8x to the 7th plus 2x and use synthetic division and divide by x minus 8, right? Do that long division, and then that remainder, right? We get our remainder down here, remainder something. That remainder would be the same as plugging in f of 8. So that is how we could use this. It's a very, very interesting result. It's very nice. So I wanted to share that with you. Now, there's one more thing to consider here. Oops. Yeah, sure. Let's do it this way. One more thing to consider with this result. Okay? And so I want to include that here too. Let's move this over. What would happen if r of x is 0? What if r of x equals 0? What does that mean? If r of x equals 0, so let's start right here, right? Let's say we do the division problem, or we do synthetic division, right? Because that's the fast way to do these. And we get p of x equals, and we have our x minus r times q of x, times q of x plus r of x. But our r of x was 0. We got no remainder. Well, that means then that really what we ended up with when we did that divide by x minus r is just q of x, right? So in other words, p of x can be written as x minus r times q of x. Well, that means q of x is a factor of p of x, and x minus r is a factor of p of x. A bigger thing would be to say that x minus r is a factor of p of x. So in other words, we can go further with this, and that is to say if p of r let's say if P of R equals 0, then x minus R is a factor of P of X. And that's the last big result that we want to take away from this. If you plug a number into a polynomial and you result as 0, well, x minus that number as a factor will be a factor. So that's really, really interesting. That helps us factor some larger polynomials that maybe we would have had trouble with before. If we know where a 0 is, we can do this. Okay? And so that is the lesson here. We're going with couple results. That, and really that comes from if P of R if x minus R, we're dividing by x minus R, then P of R is that remainder, right? So if the remainder is 0, well then x minus R is a factor. So very, very cool. All right, that's it. I hope that was useful. Hope you find that neat. And until next time, enjoy doing math.